one of the things that we saw on Monday is the central limit theorem, which said that right. So here, like if we had a sequence of independent random variables, I mean, of course, on Monday we looked at independent Bernoulli random variables, but the central limit theorem applies much more generally. Okay, now this is more general than just okay, so it's way more general than just Bernoulli trials, but there are some constraints. Okay, so there are some technical constraints. But if you have x1 through xn to be independent Bernoulli random variables, then x1 plus x2 all the way through xn divided by square root of n, the distribution of this quantity, it converges to a normal random variable with a mean equal to the square root of n times the mean of any single random variable. Okay, and the variance is okay. Uh, Sorry, I know I got cut out. Right. 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 Okay. So and it's still recording. Okay. So right. So this is not the average, but it's like a scaled version of the average. Okay. Now the scaled version of the average, it converges to something called a normal distribution. Okay. So the normal distribution, it's also called a Gaussian. Uh, okay. So this is like the typical bell-shaped curve that appears, and because of the central limit theorem, it appears in like all over the place. Okay. So specifically the PDF, so it's a continuous distribution. So if we say x is normal with mean mu and variance sigma squared, okay, okay, so if x is a continuous random variable, okay, and x takes on all values from negative infinity to positive infinity, okay, x could potentially take any value from minus infinity to plus infinity. Okay, uh, so if x can potentially take any value from minus infinity to plus infinity, it's a and it's a continuous random variable with a normal distribution. Okay, so then we specify it by means of its PDF. Right, so the PDF of x. So this is okay. At any point x will be 1 over square root of 2 pi sigma times 1 over square root of 2 pi e to the negative x minus mu square divided by 2 secant square. Okay, so this is the PDF. Now, the PDF, when if you plot it, it's like the curve that we saw the other day. It is centered on the mean, okay, and the width of this curve, how squished or how expanded it is, it actually depends upon the variance. Okay, um, so this is the Gaussian, and this happens to be the limit of most of these scaled averages. Okay, so what happens in the physical world is, like, uh, whenever we see a phenomenon that follows because of the contribution of many smaller events. Okay, so thermal noise is a very good example. Okay, so here, like, it comes from the behavior of electrons in your circuit, and they could deviate. Okay, so each single electron very difficult to model, but there are many of them, and their cumulative average is what you see as thermal noise. Okay, and so a very good model for the thermal noise is this Gaussian distribution. Okay, now it is completely specified by the mean and variance. Right, and so in that sense, it is actually quite interesting. Okay, because in order to specify, we said, like, the mean is like one approximation of a random variable, the variation is another approximation. Potentially you could also look at higher moments. Okay, so the expectation of the random variable cubed, expectation of the random variable to the fourth, and so on. Okay, now in general you need all this to completely specify the random variable. In the case of Gaussians, on the other hand, okay, you just need the mean and the variance. Okay, so the mean and the variance completely specify the distribution. All higher moments are redundant. Okay, okay. So for example, with the uniform PDF, okay, if you specified just the mean and variance of the uniform PDF, okay, so let's come back to this. Like, there is something even more interesting. Let me say that first. Okay, so uh, in this particular Gaussian, right? So this limiting distribution of most averages. Okay, what we want is the mean and variance. And when you look at the central limit theorem, okay, the mean and variance are actually easy to quantify from each of these individual random variables. Okay, so the mean of the limiting distribution is square root of n over times the expectation of any single marginal, and the variance happens to be just the variance of any of xi. Okay, so good. So this is something that we see all the time. Uh, so there are, if the central limit theorem alone were the case, okay, if that was the only nice thing, okay, possibly, like, we would have used Gaussian, and because this PDF happens to be something that cannot be integrated in closed form, okay, we would primarily work with Gaussians in a numerical way. Okay, so note that the PDF is something like e to the minus x squared. Okay, e to the minus x squared cannot be integrated in closed form. Okay, so if we wanted to look at probabilities of intervals, for example, we can compute it numerically very easily. We can do very good approximations, and when you ask for these probabilities in Python or R or any of these softwares, they compute it numerically, and you get very, very good numerical approximations. Okay, but in general, you could not do this in a closed form. So you couldn't integrate in a closed form. Okay, so if somebody asked us what's the probability a is less than x is less than b, okay, we would want to do this integration. Okay, um, maybe- right. So this is the integral we want. Okay, but there's no closed form analytically. Right. So in general, we compute this integral numerically. Okay. So the indefinite integral does not have a closed analytical form. Okay. So it's not a big deal. We can work with this. But there are certain other properties of the Gaussian that are very, very spectacular. Okay. So it is particularly useful when when we have multiple Gaussian random variables. And for this reason, like it is very common to work with Gaussian random variables wherever we can. Okay, if it is a reasonable assumption to work with the Gaussian random variables, we really want to do that. Okay, uh, so uh, any questions about what the PDF is and so on? So the PDF is just a function, right? And the function is given by this expression, right? So e to the something that grows not just exponentially, but e to the minus x squared. Okay, so it decreases to 0. So f of x, when x goes to either plus infinity or minus infinity, it diminishes to 0, and it diminishes to 0 pretty quickly. Okay, it never actually gets to 0. Okay, but it reduces very fast. Okay, so bulk of the mass is concentrated around the mean. Okay, and usually this quantity, the square root of the variance, this is the standard it's called the standard deviation. Okay, and usually if you go like 2 or 3 standard deviations away from the mean, okay, you pretty much have very low probability of seeing anything beyond this. Okay, uh, okay, so you'll sometimes see people uh, give you guarantees like 5 sigma guarantees, 3 sigma guarantees, and so on. It's somewhat common to say things in that way. That means that you will not uh, that means that you're going to somehow ensure that within 3 standard deviations or 5 standard deviations away, your guarantee holds. Okay, so the probability that your guarantee is violated is very, very small. Okay, so that's kind of so what you want to say is that um, under so the so when you say like you give like a very good guarantee, right? So what it means is that like here is a random variable. The random variable technically could take any value from negative infinity to plus infinity. You cannot rule them out. Okay, but what you can say is that if you know the mean, you won't go far away from the mean with very good confidence. Okay, so even though like something like mu plus 10 trillion is a possibility, okay, chances are you'll not see those. Okay, so the probability that you see a value beyond 3 standard deviations from the mean is actually very small. It's something like 0.01%, or like the probability is maybe the probability is 0.01. Like 5 standard deviations, the probability you see some value beyond 5 standard deviations, something like 0.001. Okay, so that means that even though the random variable technically could take any value from negative infinity to plus infinity, it for the most part you're not going to see very extreme values. Okay. Okay, so good. So this is like very basic about a Gaussian. Uh, we also have we also have this notion of a standard Gaussian. Okay, and the standard Gaussian is corresponds to the special case where the mean is 0 and the variance is 1. Okay, it's some kind of a normalized Gaussian. Okay, so in general, if x is a Gaussian with mean mu and variance sigma squared, okay, then the quantity z, which is x minus mu divided by sigma, okay, has okay. So if you have any Gaussian distribution, if x is any Gaussian random variable, okay, there's a way to normalize it. Okay, because no matter what the value of mean or value of the mean mu and the variance sigma squared, okay, the properties of the Gaussian doesn't really change. Okay, so there's one standard normal way. I mean, there's one way to normalize all of this, and that is what is called this z-score, or it's commonly called the z-score. Okay, so what we do is we take this auxiliary random variable, we subtract out the mean x minus mu, but we also scale it by dividing by sigma. Okay, now when you look at z, okay, the expectation of z is the expectation of x minus mu divided by sigma. Okay, and take out sigma, and here we have, right, so this is because the expectation of a scaling times a random variable, expectation of any constant times a times a random variable x is a times the expectation of x. Okay, and the linearity of property of expectation then means that this is divided by sigma. The expectation of a constant is just the constant. Okay, because if a constant, you can interpret it as a random variable that is equal to so the constant mu, you can interpret it as a random variable that is equal to mu everywhere on the universe. Okay, and therefore its expectation will be mu again. Okay, so this will be the expectation of z, but since x has mean mu, okay, this expectation is 0. Okay, and the variance of z is the variance of x minus mu over sigma, is 1 over sigma squared, the variance of x minus mu, which is 1 over sigma squared, the variance of x, which is sigma squared over sigma squared, which is 1. Okay, so this is all we are saying. If x is a Gaussian random variable with mean mu and variance sigma squared, then if I look at the random variable z, okay, z has mean 0, okay, and variance 1. Okay, what is interesting is that z will also be Gaussian. Okay, the distribution of z will also be Gaussian. Okay, we can use like the stuff we know about transformation of random variables to infer this, but rather than worry about the computations, we are going to note a property of Gaussians which is even stronger than this. Okay, and this is one of the core reasons why we like to work with Gaussians all the time. Okay, so for now, like we want to just take for a fact that if X is say Gaussian with any mean mu and any variance sigma squared, okay, then there's a way to normalize X, okay, by subtracting out the mean and dividing by the standard deviation so that you get a standard Gaussian, that is mean 0 and variance 1. Okay, and this is important because most of the computations we do numerically, and right now, like we can just feed it into a computer, it's not a big difference. But in the past, the way people would do these integrals was they would look up tables. Okay, now when you're going to look up tables to do integrations like this, okay, so there is no reason to print a separate table for every value of mu and every value of the standard deviation. Okay, so what people would do in the past, which is not so relevant anymore, I guess, but what people would do in the past is like you would get these tables of Gaussian distributions. Okay, that would tell you a bunch of integral values. Okay, for specific values of a and b. Okay, now from those integral values, what you would do is you take this random variable x, convert it into a standard normal, okay, and you would have these tables which tell you all these integrals for various ranges of a and b for a standard normal. Then you would look that up to compute this integral. Okay, now of course the whole point is moot now, like you can directly feed it into Python and it will do the it will do these calculations for you. But it's good to know that in the past, like how people used to do things. Okay, and it's also important to know because today, like when we work with Gaussians, when we have to work analytically, okay, we write many of these quantities in terms of these integrals. Okay, so we leave it in terms of these integrals. Okay, so you will find like statisticians always say something called the error function. People in engineering always say something like the Q function. They are both specific integrals that correspond to these Gaussians. Okay. So any questions? Just a second. Right. So any questions so far? Okay. So when you have a okay, so suppose Z is a standard normal. Okay, in engineering, okay, the integral that we try to express whenever you're working with Gaussians, right, you'll have all these integrals that we do not know how to compute. Okay, so we define this function q of x. Okay, and q of x is defined for positive values of x and negative values of x. Okay, and it's the integral from x to infinity of the Gaussian PDF. Okay, so this is q of x. Okay, so q of negative infinity. So what will be q of negative infinity?
That's just 0.
No. So Q of negative infinity will be the area under the PDF overall.
Oh, sorry, I was looking backwards. 1.
Right. Right. So it's the area under the PDF, and area under the PDF is always 1. Okay. And Q of infinity is 0. Okay. And Q is monotonically decreasing. One property about Gaussians is that if you look at the PDF of a standard normal, okay, so this is mean 0, variance 1. Okay, so 2 pi sigma is 1. So I just leave a 1 here, and e to the minus z minus 0 squared over 2 times 1. Right, so if you substitute mean 0 and variance 1 into a standard normal, I get 1 over square root of 2 pi e to the minus c squared over 2. Okay, so this is the PDF. Okay, this is symmetric in z. Right, so this is symmetric in z in the sense that if it's symmetric around the origin with z. So if that means that fz of z is the PDF at negative z2. Okay, so if I take a point here z and I take another point negative z, okay, the value of the PDF, okay, I haven't drawn it properly, but the value of the PDF at these 2 points at z and negative z, they have to be equal. Right, so that means that this function is symmetric around the origin. Okay, so with that in mind, what is q of 1/2? Sorry, what is q of 0?
That would be 1/2,
Right.
0.5.
Right. So this is 1/2. Okay, because the area on the positive side uh, uh, of z will be equal to the area on the negative side of z, and together they sum up to 1. So q of 0 must be 1/2. Okay, so any so so suppose we wanted the integral from a to b, okay, of the PDF. What would this be in terms of the q function? Right, so this would be something, so I write it as a to infinity of fz of u du. So I'm going to use different dummy variables. Minus b to infinity of fz of v, right? So we could write this integral over this interval a to b as the difference between these two integrals. Okay, and so this is just q of a minus q of b. Okay, so if somebody tabulated all the values of q for sufficiently good granularity of a, okay, you can't do it for every value of a, but maybe with for different values of a with very small intervals, okay, then you could compute any integral like this using the table. Okay, and so that's what people used to do in the past. Okay, um, so so this is about like basically what a Gaussian is. Okay, the first thing you learn when you go beyond an undergraduate course, okay, when you go a little bit beyond an undergraduate course in engineering, is just how powerful these Gaussians are. Okay, and it particularly comes about when you have multiple Gaussians. Okay, so whether we are looking at communication setup or whether we are doing something like linear regression, so whether you're doing machine learning or whether you're doing communications or something like that, right? It is the situation is that you generally have a bunch of these random variables which you model them as Gaussians. Okay, so Z1, Z2 to Zn. Okay, suppose they are Gaussian. Okay, now it is possible. Okay, so they could. So now we are asking something about the joint distribution too. Okay, uh, so each of Z1 through Zm is a Gaussian random variable. Okay, now even though each of them is individually a Gaussian random variable, that is usually not, that by itself is not the important case for us. Okay, what we want is like something about the joint PDF. Okay, we don't necessarily want them to be independent. Okay, so but we want them to be something called jointly Gaussian. Okay, what it means is that you have Z1 through Zm, each of them is Gaussian. That is not enough, but you also want every linear combination of Z1 through Zm to also be Gaussian. Okay, so the definition is something like this: Z1 through Zm are jointly Gaussian. It's not something that always happens, okay, but it's something that we like to model things as. Right? Okay, so there is a way to characterize when you have joint Gaussianity, okay, but that is one of the first things we look at, okay, and indeed this stronger notion, not just that each of these random variables are Gaussian, but together they interact in a way which is just right, okay, they interact in a way such that every linear combination of them is also a Gaussian random variable. Okay, and from the definition itself, like here is what you see: very closely affiliated with Gaussians is this notion of linear algebra. Okay, so in fact, like all linear algebra results that you learned in 307, okay, particularly with respect to linear regression and so on, okay, they have one-to-one analogs with Gaussian random variables. Okay, so uh, so in many ways, uh, uh, we do a lot of things that are linear in engineering. Okay. So far, you have been told that one of the reasons you look at linear models in engineering is that it's something inspired by the Taylor series. You say, okay, the linear, this one, it's the first order approximation for a system. Okay. But the reasons go a lot deeper than that. Okay, what happens also is like when you're looking at it in a probabilistic setup, okay, the central limit theorem or something like that would apply typically. Okay, and so the characteristics that you're looking for would be modeled as a joint Gaussian random variable. Okay, now when you have joint Gaussian random variables, you have this very interesting property that your best estimators, okay, of are always linear. Okay, you're guaranteed that your best estimators will always be linear. Okay, and so this is like uh, this is like a minor miracle that happens here when Z1 to Zn are jointly Gaussian. Okay, when Z1 through Zn are jointly Gaussian, okay, what is the best estimate in general? What is the best estimate of z1 from z2? In general, what would be the best estimate?
Expectation of z1 given z2.
Very good. So it's the expectation of z1 given z2. What is the best estimate of z1 from, let us say, z2 and z3? The best estimate of z1 from z2 and z3?
z1 given z2 and z3.
Very good. Right, and so on. So this we know. Okay, this happens in general. But in the Gaussian case, okay, this expectation of z1 to given z2, which is in general a function of z2, okay, is a linear function of z2. Okay. Okay, the expectation of z1 given z2 and z3 is a linear function of z2 and z3. So it is alpha, so let's say alpha prime z. Okay, so what happens is, like, when you're estimating, when you have a bunch of jointly Gaussian random variables, when you estimate one random variable from the others, okay, your estimates are just linear functions. Okay, so here automatically the linear thing is the best thing you could do. Okay, there is no advantage to looking at nonlinear functions when you're estimating one jointly Gaussian random variable with another. Okay, this is actually the deeper reason why we like linear methods. Okay, and it is a direct consequence of this property. And so this is kind of like a little miracle that happens when you have a bunch of Gaussians that are jointly Gaussian. Okay, now characterizing joint Gaussianity, it's a little more complicated than what we know so far. One thing we do know is this, one thing that we can say right now is that if z1 and z, if a bunch of Gaussians are independent, they are also jointly Gaussian. In a sense, this is not terribly interesting. I mean, if you have independent Gaussians, they're also jointly Gaussian. Not so interesting because we really want the case where we want to estimate one from the other. Okay, and if they're independent, they're not telling you any information. Okay, so this is kind of the trivial case where they're jointly Gaussian. Okay, nobody is giving you anything, so all these estimates are just constants. Okay, so this is not terribly interesting, but joint Gaussianity is a lot wider than just independence, luckily. Okay, so even when z1 through zm are dependent, they could be jointly Gaussian, and that is precisely the case we are most interested in. Okay, because then you can estimate one random variable from another meaningfully. Okay, and your estimators there will be linear. Okay, they're guaranteed to be linear. Okay, so we will uh, uh, we will just stop here. Like, this is the first topic you look at in, like, any future course of from this point on. Like in 640, for example, you'll spend a lot of time on these Gaussian random variables. Okay, so it has, like, consequences of this. There are a lot of very interesting consequences. If you have a single Gaussian and you're trying to estimate the mean and the variance, okay, it will turn out that the mean and the variance happen, your estimates will be independent always. Okay, so So basically, the point is like these Gaussians, even though it comes with a PDF that we don't know how to integrate, it has a lot of like really fantastic properties that makes working with them very easy. Okay, so wherever we can, we try to use Gaussians. Okay, so in real life, like so when you look at 343, you're going to look at you're going to model thermal noise as Gaussian. Okay, when you look at either 345 or 445, you'll be doing linear regression. Okay, and the version of the probability model that fits into linear regression to give you interpretation of what is significant, what is not, they are Gaussian models. Okay, so so whether it is from like more traditional communications or traditional statistics or like the newer machine learning formulations, okay, you will be using some variant of these assumptions all through. Okay, now it's not so each of them, like you don't use them in exactly the same way. You fit it to the problem and you analyze the situation based on the problem at hand. So the analysis in a communications course will be different from what you would do when you learn Gaussian processes, for example. They're all different. Okay, but underlying all of them is this are these Gaussians that kind of are like the ideal model for most problems that we look at. Okay, for or rather the ideal model we would like to have for problems. It's not always appropriate, but it's a model that we are very happy if we can use. Okay, so we'll wrap up here. So what we'll do is like so we are almost out of time too. So but we can. I'll also add a couple of other practice quizzes. Okay, but make sure to do all the quizzes. Make sure you understand how to do all the quiz problems. Okay, once you understand them, like if you understand them, your grounding in all this probability, it's actually very good. Okay, the other thing is a little more logistical thing is like so. I don't know, Justine is here. Like some of you are asking how to submit like the quiz solutions. Okay. So you can submit any quiz problem, and I'll use that to make up for your for your credits in other sections. Okay. Send it to me by the Thursday on the finals week. So that is not 2 days from now, but 9 days from now. Okay, and I'll use that to make up for your grades. Okay, for some of you in the midterm, I've asked you to right, 8 days. Yeah, today's already Wednesday. Yeah, so for some of you, I've asked you to submit some midterm problems. Not, I mean, if I haven't mentioned anything, you have to submit both the problems. But for some of you, I've said, okay, submit this part or that part or so on. So just submit the parts that you've been asked. Okay. For those of you who, for whom, like I've only asked to submit like uh, part of like one part or something like that. So even if you don't submit, you'll get most of the 12 points, the 12 bonus points, but it's sort of amortized. Okay, so just submit that part. So those are the parts where potentially there was a mistake. Okay. Uh, okay. So any questions? So on also Friday, we'll look through all the material and sort of review anything you want to review. Okay. So any questions?
Fridays at what time again? Is it still 10:30?
Yeah, we can. Yeah, so let's do it the same time, just because there are possibly no conflicts. But also, like Fridays when there will be the 496 presentations and so on. I don't know how many of you. Right. So just let me just email me and so, but it's in the afternoon, right? If I remember.
I believe it begins at noon and then goes until 2 in the afternoon.
Okay, so this time would still right. Okay, so this time would still I mean it is somewhat of a conflict because it's right before your presentations, but it's at least not directly in that time. Okay, so we can keep 10:30 to 11:30. Okay, or if many of you strongly prefer, we can move this to 9:30 as well. Okay, so but I mean it's probably better to avoid confusion. We'll just keep it at this time. Okay. Yeah. Okay. So any other questions? Okay. So good. So I'll see you. I'll see you all. Like the Friday class is optional, but I'll see. Whoever wants to come on Friday. Okay. The just a reminder. The finals is Monday at 9:45. So it's going to be 2 hours. So just to recap, like so, just so we don't look up the wrong time in the finals. Okay. So Monday at 9:45 in the morning. Okay. Okay. So I'll stop recording and everything, but you can ask questions and so